Hello everyone. So today is gonna be our day 36, and so we are continuing the DSA sheet, right? And the question that we're gonna solve today is flattening of a linked list, right? So let's read the question. So obviously I this question is probably not on lead code. That is why the link given here is of GFG. So yeah, we can solve it on GFG until unless as long as we are able to solve the question, that's what it matters, right? So yeah, given a linked list of size n, where every node represents a sub-linked list and contains two pointers, a next pointer for the next node, a bottom pointer to a linked list where the node is head. Each of the sub-linked list is in sorted order, right? This is important, right? Flatten the linked list such that all the nodes appear in a single level while maintaining the sorted order. Note, the flattened list will be printed using the bottom pointer instead of the next pointer. For more clarity, okay, blah, blah, blah. So, yeah, this is the question, right? So, see, until now, what we know is that there is a linked list that exists like this, right? 5, 10, 45, whatever, 25, pointing to null. It is a single linked list, right? But if this particular node also has a pointer called bottom, let's just say, which has 17, right? And or any other node, let's just say 23. But there is something that to be noted is that this list is in sorted order. And if this also has a bottom, if this also has a bottom, this also has a bottom, it will be sorted. That's what it is given in the question, right? What we want is at the end of the day, we want this list, right? This link, this given input, this is the input, right? So what we want is we want the first element to be the smallest. Let's just say I think 5 will be the smallest. So 5, then probably 7, then 8, then and dot dot dot. I mean, it should be in sorted order. That's what it says. That the flattened list will be printed using the bottom pointer. So everything should be on the in the bottom thing, and the next should be pointing to null for every node, right? For this node as well, it will be pointing to null. So how can we solve this question, right? So 5, 10, 5 has these many things in the bottom, 10 has these many things, 19 has these many things, 28. And thing to be noted is that these nodes in the bottom part, right? They are all sorted. In the horizontal part, they might not be sorted, but in the vertical part, they are obviously sorted, right? Okay. So the brute force, like let's just see what the brute force is. It's not W, it's N, right? Brute force is like, hey, I just can do one thing, okay? I can traverse. Let's just say if this is the, given, if this is the linked list given, what I can do is I can simply just say that, hey, I can probably keep my temporary variable here since head is this only, right? Head is this only. I can check if there is bottom, right? I can do one thing. If this is temp2, right? This can go down. Okay. So if this is an what do you call it? An array, right? I will take an array. So 5, then temp2 comes here, then 7, then 8, then 30, right? Because T2 will come here eventually. And next is null. So what we'll do is we'll move our temporary to this point, right? Now, if this has a bottom, we'll take a temp2. This will again say like 10, then again temp2 will go here. It will have 20, right? Then what? Then next is null. So temp comes here. Then 19, 22, right? 22. 50, then 28, 35, and all these. Basically, I hope you understand. And then what we can do is we can have a dot 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 here. Next thing, we can sort it up. We can sort this up. You can use any sorting algorithm. The best one will be obviously taking n log n, right? And then we can sort it up. And what we can do is we'll have a sorted array, right? This will be a sorted array. So first will be 5, then will be 7, then will be 8, then will be something, 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 right? So all the things will be in sorted manner. Now what we'll have to do is we'll have to convert back to linked list, right? So this will how our naive solution look like. Let's kind of discuss the time complexity, right? Let's go over every step. So what is the first step? We are traversing everything, right? So O of n, that is the length, that is the horizontal length of the linked list, into we are traversing the vertical part as well. So let's just say if n is horizontal, and m is vertical length, right? So n into m will be our uh, time complexity to traverse plus, okay? Okay, this is one part. Then we are sorting it. So sorting takes O of, let's just say, a bigger n log n, where n is nothing but n into m, right? N into m plus. So sorting is done, right? Now converting this back to a linked list. Again, it will take O of n into m, or simply just a bigger n, right? So overall, it takes O of 2n plus O of n log n, right? This is what the space complexity is. Now, sorry, time complexity is. Let's kind of discuss the space complexity as well. See, we are taking an array. We are taking an array, right? So that is O of bigger n, where n is equals to n into m. Okay. But we are also converting back to linked list. Now that is also again one bigger n, because this takes array. This is the space for array. This is the space for linked list, right? This is the space for linked list. So again, it is O of 2n, right? Okay. So this is what the time complexity and the space complexity for this algorithm looks like. And I hope you obviously can, kind of write the pseudocode as well as the main code in your language, because it's a very easy implementation. It's a very easy implementation. But the point is, if we have to optimize, then how will we do it, right? This is our query. This is our point. Okay. Let me just paste it here. Cool. Can you notice one thing? Can you notice one thing? These things are sorted, right? These things, in fact, including this, and this. All the vertical parts are sorted. I did not use that because I see if it is mentioned in the question, that means it will be used somewhere, right? This is hint 101. This is hint 101. That if something explicit is given in the question, that means it has to do something with the algorithm. It has to do something with the optimization, right? So if this is the point, then can I use that to in my defense, or in my advan what do you call that, right? I can basically use that, right, to my advantage. Okay. How can I use that? How can I use that? Let's see. Let's see. Okay. Uh, can I do one thing? Can I do one thing? Okay. Mm, let me paste it again and delete some of this. Okay. Just give me 1 second, okay, so that I can kind of delete few things. What if I delete this? I am just left with all these things, right? I am just left with all these things. So let me bring it a little. Yeah, cool. I am just left with two linked lists, right? Two linked list. Now this can be list one. This can be list two. Okay. Assume this is the head, right? This is the head, and not even head. You don't have to worry about the head, right? Let's just remove this. This is this is list one, and this is list two. Remove this also. Okay. If two individual lists are given to you, can you merge them? And assuming both the lists are sorted. If you remember the question, if I go here, merge two sorted linked list, right? Merge two sorted linked list. Can we do that? I think we can, right? I think we can. Let's see how we can do that. Let's say I have a temporary one here. I have a temporary two here. No problem. Okay. I will compare if my 19 is greater or smaller than my 28. I have a dummy node, right? If you remember, we used to take a dummy node, right? Now, why we took a dummy node? Because we are kind of creating a separate a separate list altogether, although we are using the same nodes that are given to us in both the list, but we have to take a dummy node. Why? Because we are kind of creating a new path, right? If you remember, I have explained to you why we use dummy node probably more than 3 times now in different questions, that we have to use a dummy node. I mean, it is better to use dummy node, so that what you can, at the end of the algorithm, you can just return the head as dummy node dot next, right? This is what we did. Great. So what I can do is I can say that, hey, in this particular question, in this particular question, I know that there will be one more pointer called bottom. So this is also pointing to null right now. Cool, no problem. What is lesser than? What is what is less? 19 or 28? You will say obviously 19. Then remove this and have 19 here, right? Obviously this will point to this particular node only, but right now I'm just writing it here. We will reuse the nodes given to us only, so don't worry about it, right? Okay. T1 moves from this to this. T2 is there only. 22 compared with 28. Okay. Obviously, 22 is lesser. T1 moves here. 50. Oh, obviously 28 will come because 28 is lesser, right? So 28. T2 moves. T2 comes here. 35 or 50, whichever is less. 35, obviously. So 35. Cool. T2 moves. T1 or T2, which one is smaller? 40, right? T2. So 40. T2. Which one is smaller, 45 or 50? You will say, hey, obviously 45 is smaller. So 45 comes here. I don't know why my mouse is like that. Okay. Now T2 moves to null. T2 moves to null. What was the thing that we did now? If T2 is null, we break out of the first loop and then we check if T1 is not null. That means we'll have to join everything that is left in T1 to my pointer, to my dummy nodes pointer, to my temporary pointer. Correct? This is what we used to do. Because I know that it is in sorted order, if this 45 was not greater than this T1, how the hell will all the other other elements left in T1 will be greater, will be smaller, right? So that is why we just simply join T1. So joining T1, that means we have 50 and then we have null. Can you see one thing? Starting from -1, then comes 19, 22, 28, 35, 40, 45, 50, and a null. Isn't this in the sorted order? Sorted, right? This is sorted. This is sorted. If I have combined this to be a single linked list, can I now take this as list 1 and this combined list as list 2? And can I do that? I can, right? I can. This is list 1 and this combined, these two as combined, what? This answer can be combined to this, can be combined to this, correct? Yes, it can. Yes, it can. Okay. Now, assuming that these two now are combined, these two are now combined, can I take this as list 1 and this whole as list 2? Yes, I can, right? And eventually you will see that this whole will be now called as list 1, as in it will be a singly linked list in the vertical manner. And this will be sorted, right? This is what we used in merge to a sorted linked list, and this is what we're going to be using this. Okay. Let's just not write this pseudocode right now because we'll just do it in the code editor, obviously. Let's discuss the time complexity for this, right? Let's discuss the time complexity. What I'm doing is I am traversing this whole linked list, right? So O of n into, I am traversing this O of m. Am I doing anything extra? Am I doing anything extra? Merging and everything is inside it only, right? Because I'm traversing, I'm checking which one I am traversing. List 1, I am traversing list 2. I am just checking which element is smaller. In that moment only, I am traversing the O of m. That is this length in the vertical manner. That is how I'm traversing it. And this is when I'm traversing when I'm comparing the two lists. This is O of n. When I'm joining them, this is O of m. That's it, right? Space complexity. Am I using any extra space? No, I'm not. This is being done in constant time. Great, great, great. Can we write the code now? Let's do one thing. With every line of code, I will do one thing. I will just write the code. I will explain to you, and then I can, writing pseudocode will not make sense because we have already done this question earlier. We just have to write the recursive solution for this, and then we'll just call that function that we have already written for merge to sorted codes, right? Merge to sorted linked list, sorry. Okay. If head that is given to me is equal to null, or head dot next is equal to null, can I return the head? Why am I saying that? If the given head is null, that means I am returning null only. Okay. If head dot next is equals to null, that means what does that mean? That I am on the last node because this dot next is null. That means this will be my list 2 and the one previous will be my list 1, right? This can be inferred from this that, hey, I am on the last node. So whatever you have to do, you just have to return because this is your base case. This is your base case. You cannot go further, right? So I can write that this is my base case. Okay, cool, right? We have written this. Now, what is another thing? Now, the other thing is that I have to merge. I have to merge these things. Okay. But how can I do that? How can I do that? Okay. Mm, can I say that, hey, if my head was here, I will have to move my head to this point, then to this point. As soon as I reach here, then I'll have to perform what? Then I'll have to perform the merge to list. So I can say that hey, head is equal to flatten head dot next, right? This is how what I can do. Sorry, not head. Head dot next is nothing but head flatten head dot next, right? Right. Because I'll tell you, see what I'm trying to do here, right? This is this line. I'm saying that hey, I know that if 5, 7, they are 7 and 8 and null. This is let's just say this is 30. This is null. This is null, and we can take 10 here, right? We can take a smaller. If this is my head, what is my head dot next? It is nothing but I have to say that hey, if this is f function of 5, what I'll have to call? I'll have to call f of 7. Then what I'll have to call? I'll have to call f of 8. Can I go further? Because this is my last node, or this is my last list, right? After that it is null. That means at this point will be my base case being reached. So here I can say that hey, merge. What can you merge? You can merge, this is my head, this is my head dot next, this is my head dot next. That is why I have taken head dot next is equals to flatten head dot next, right? Okay. Now, I can say that, hey, head, what you are doing is merge two sorted lists where I can pass head and head dot next, right? And I can simply return the head, right? I can simply return the head, and I'll have to use this dot here because this is a class-based implementation. And let's just simply write our function for merge two sorted lists, which will take list 1 as their head and list 2 as the second list's head, right? Now this we have already done, so we will not take care of it, and we don't have to return the head. We have to return the head dot bottom, I guess. But yeah, we'll see, right? See, let temp1, or let's say let dummy node is equals to new node, where this is minus initialized with -1, and let temp is equals to dummy node, right? It is pointing to dummy node. While I can say that hey, let t1 is equals to list 1, t2 is equals to list 2, right? While t1 is not equal to null, and t2 is also not equal to null, if t1 dot data is less than t2 dot data. Now, what does this mean? That means the the temporary one's data is lesser. That means it should be the next point. It should be the next point. So temp dot bottom will be pointing to what? T1, right? T1. Temp should move ahead. That means temp is equal to temp dot bottom. And T1 also should move ahead. T1 dot bottom. Else. Else, that means temp dot bottom is equals to T2. Temp will move ahead. T2 is equals to T2 dot bottom. That means T2 also moves ahead. If T1 is still existing, that means temp dot bottom should be equal to T1. Else temp else we don't have to check else. We can just say if temp2 is there, we can say that, hey, temp2 dot bottom, you can point to temp2, because either of one will be obviously exhausted. And what we can return, we can simply return uh d node dot bottom. Correct. And let's see what it returns. Let's see what it returns. Your output, expected output, right? So basically, we have written the code in one go. Let's try to submit it. This question has been solved, right? You get, okay, basically I've already solved this question here. So I don't think this will be marked as here, but yeah, you can see that, hey, test cases have been passed, right? Can we understand this logic again? Okay. What does this base case mean? Hey, if head is equals to null, that means I have an empty list. That means I'll have to return the head only, or maybe null, doesn't matter. Or else, if head dot next is null, that means I'm on the last node of an existing list. I'm on the last node of an existing list. That means that is the point where I have to return that whole node. Now, why I have to return the whole node? This line will explain to you that. I know that my head dot next, that is, or I can write head dot next signifies list 2, head signifies list 1, right? Head dot 2, head dot next signifies list 2. That means the list I was talking to, right? This is the list that is head dot next, correct? If my head is here, I can reach to this point, but if my head is here, can I reach to this point? No, right? I'll have to keep a point here. I'll have to keep a point here, then only I can move forward, but I cannot move backwards, right? In a linked list that you already know. That is why I can say that, hey, head dot next, you are nothing, but you are nothing. Or I can simply say that, hey, what it will return me? It will return me merged head. It will return me merged head. That means, see, if I am given this 28, 35, 40, this is the only input that is given to me. Isn't this already sorted? Isn't this already sorted? Do I even need to sort it even further? No, right? That means I can simply return this. This is what it is doing. This is what the base case is, right? So this is a merge head ideally, and I can call that, hey, head. Why head? Because I have to combine it to only single list. That is, the head will be nothing but list one, and list two's merged head will be head, right? So I can now, here I can say head dot next, you can be merged head, right? And I can simply at the end, because I know at the end of the day, this whole thing will be merged into one into one, and the first element will be nothing but head. That means I'll have to return head only. That is why I'm returning head here. And we can simply, if I check, compile and run, I'll get the same answer, correct? So merge head, you can obviously understand in this manner also, right? You can understand in this manner also. So yeah, I hope you understood the question. What you have to do is you just have to take a pen and paper and you just have to understand it, right? Just start. What is recursion at the end of the day? If one thing can be, if we have 10 things to solve, right? If we have 10 things to solve, we can we can pick one thing and we can solve that. If all the 10 things are being solved in the same manner, right? We can ideally solve it by recursion, right? We can ideally solve it by recursion. Now, how can we do that? We can simply solve everything We can solve everything and take a base case over there. This is what recursion is, right? This is what the power of recursion is. If you can solve one thing, you can solve 10 things, right? Just consider that one thing as the base. That hey, if if I was given this kind of a list, I was given a single linked list with having bottoms and next would be null. What would be my answer? I would just simply return that because I know that is sorted. If I take another list with it, that means now I have two lists. Can I combine them into one? I can. I can. We have done this question already called merge to sorted linked list. If I can, if I can resolve it into one, right? Can I do three things? I can resolve two things. I can resolve two things, make it as one, and then I can resolve this third thing. I hope you can see my fingers in the camera. If I have three lists, right? If I have three lists, I can resolve two lists out of them with the question called merge two sorted linked list. Now I have only two lists left, list one and list two. Now resolving them, now I have a single linked list. Now I have a single linked list with bottom, right? And next is equals to null. This is how the question will be solved. This is how you build the intuition for this question, right? We can write notes here. Using recursion, we can solve it by taking the help of merge to sorted list. If we can solve merge, if we can solve two sorted lists and convert it to a single list, then we can do that for the whole given input. Simple, right? Let's just save it, remove this, and mark this as done, right? So, yeah, this was the question. This was the question. Take a pen and paper, do whatever you have to do everything on the paper. You will eventually understand everything. So, tomorrow's question will be rotate a linked list. I'll see you tomorrow, guys. Bye bye. Thank you so much for joining in.